Hey guys, here we are, 5D, 2 marks here. In the previous problem, 5C, we showed that z squared star is equal to z star squared. And in the problem before that, we showed that z squared, which was 5 minus 12i, negative 5, plus 12i had roots. Okay, we showed that z equaled negative 2 minus 3i, and z also equaled 2 plus 3i. So I'm going to show that the roots of this are equal to the complex conjugates of those, which would be the roots of negative 5 minus 12i would end up being negative 2 plus 3i and 2 minus 3i. Let me show that real quick. So I know that z squared equals negative 5 plus 12i. And if z equals negative 2 minus 3i, then the conjugate of z would be negative 2 plus 3i. And since the conjugate of negative 5 plus 12i is negative 5 minus 12i, then that shows that this is one of the roots. Okay, now the other way around, instead of doing this substitution, I could have done this substitution, which would mean that the other root for negative 5 minus 12i would be 2 minus, whoops, this should be a negative 2 plus 3i. Oh, I'm sorry, no, never mind. 2 minus, that should be a plus, 2 minus 3i squared. Therefore, you can see that the two roots of negative 5 minus 12i should be the following. Okay, let's move on to 5e. Graph of the polynomial function f of degree 4 is shown below. Explain why of the 4 roots of this equation 2 are real and 2 are complex. Well, we can clearly see the real roots. So the real roots are x equals negative 4 and x equals 2. Since there are only 2 real roots, then there must be 2 imaginary roots or complex roots. I'm gonna go ahead and assume we're gonna do that in the next part. Okay, so the curve passes through the point negative 1, negative 18. Find f of x in the following form. Well, first, what I do know is that these 2 would be real roots, which I knew happened at negative 4 and a positive 2. So f of x would equal x plus 4, x minus 2, x squared plus cx plus d. Okay, so if I plug in a negative 4, I should get 0, which won't really help me, right? It won't help me to find C and D. So what I want to do is plug in a negative 1. So this will be a 3, this will be a negative 3, negative 1 squared will be 1 minus C plus D. And I know that f of negative 1 equals negative 18. So it would be negative 9 times 1 minus C plus D. So it looks like 2 equals 1 minus C plus D. Therefore, 1 equals negative C plus D. Okay, now there's a hidden gem out here as well that we didn't talk about yet, but in this graph it looks like if I plug in a 0, I get negative 32 out. So f of 0 equals negative 32. So if I plug in a 0, 0 plus 4 is 4. 0 minus 2 is negative 2. If I plug a 0 in, x squared will be 0. C will disappear, and I'll be left with d. So again, this was negative 32. This will be negative 8. So it looks like d will equal 4. So if d equals 4, then that means c has to equal 3. Therefore, f of x will equal x plus 4, x minus 2. I don't think the order of those will matter with regards to being graded, plus cx, which is 3x plus d, which is 4. That is a 4. Okay, cool. I think I answered what they wanted. Yes, I did. Okay, now it says find the two complex roots of the equation f of x equals 0. Well, the complex roots are going to come from this portion here, so I want to know where this thing right there equals 0. It's not going to be factorable, therefore I've got to use the quadratic formula. So it'll be negative b plus or minus square root b squared minus 4 times a times c, which will be 16 all over 2a. So it looks like my complex roots will be negative 3 halves plus or minus I root 7 over 2. They're your complex roots for that polynomial. Alright, let's keep moving. Part H says draw the 4 roots on the complex plane. Okay, so I knew that I had x equals negative 4, x equals positive 2, x equals negative 3 halves plus I root 7 over 2, and x equals negative 3 halves minus I root 7 over 2. So let's draw those on an Argand diagram. Alright, here will be x equals 2. That'll be the point 2 plus 0i. This will be the point negative 4 plus 0i. This will approximately be the point negative 3 halves plus I root 7 over 2. Notice the imaginary component is positive, and then symmetrically speaking, the fourth root would be down here. Alright, awesome. Let's do part I, 6 marks here. Express each of the 4 in r e to the I theta form. Let me remind myself what I had in what color. Okay. So if x equals negative 4, think of that as, it's got a modulus of 4 and an angle of rotation of pi. So that would be x equal to 4e to the I pi. Or, you could think of it, and this isn't the right form, but 4 cis pi. All right, x equals 2. I think 2 is blue. Yes, it was. That would be 2 cis 0. So that would be 2e to the I 0. And I would leave it in that form even though that's reducible. Okay. Now in the next part, it gets a little funky. If I have x equal to negative 3 halves plus or minus I root 7 over 2, I need to find the modulus and I need to find the angle. And so how I'm going to go about doing that is I'm just going to sketch real quick the Argand diagram again from above. I think I had green above, right? So this would have been x equals root 7 over 2. Just going to sketch this triangle out. And this would be negative 3/2. Okay, so to find the modulus, this value, this will be r. Use Pythagorean theorem. So let's go ahead and do that. That would end up being, so r squared would equal x squared, or the real component squared. So negative 3/2 squared plus square root of 7/2 squared. So r squared would equal, what would that be? 9/4 plus 7/4. Oh, that's beautiful. R squared ends up equaling 16/4, which is 4. So r will end up equaling 2. And the nice part about this is r will be the same down here due to symmetry. It's just that the angle will be slightly different. So I know for x equals negative 3/2 plus root 7 over 2, this will be 2e to the I something, right? And same thing will be true for its buddy down here in quadrant 3, but the angle is going to be slightly different. So now we got to do a little calculation here. I want to find this angle, and that'll help me to find the angle of rotation there. Okay, so this right here will be my argument. My argument for, I guess you could call this the green x, right? It's the argument for the green x. And then this angle here would be the argument for the yellow x. But the really nice thing is that we only have to do a little bit of work. We don't have to do twice the work here, because these two angles will both be theta. So if I can find theta, I can find the argument for the green x by taking pi minus theta. Okay, I'm going to take the angle pi minus theta. That'll give me the argument of the green. So I'm going to kind of stencil that in here. It'll be pi minus whatever theta comes out to be. And then for the yellow one, I'm going to do pi plus whatever theta comes out to be. Okay? So let's go ahead and do a little work with how to find that angle. Well, that angle, okay, the tangent of theta will end up equaling root 7 over 2 over negative 3 over 2. Okay? Root 7 over 2 over negative 3 over 2. So if I reduce that, tangent of theta equals negative root 7 over 3. Alright, so theta equals the arctangent of negative root 7 over 3. So there you have it. In here I would take, I'm not going to write it because I'll run out of space, but I should take arctan of that and plug it in for both of those. Alright guys, that's the remainder of problem number 5. I hope it made sense. If you need help, let me know. Shoot a question. Have a great day.